Hello, Sister Science Club. So I think I said this last time I had to speak. Everybody believes in science is a member of the Sister Science Club. So you're all members, and I want to welcome you. We've got a great speaker. A little bit of housekeeping, and then we'll get to it. All right. I want to thank Angeline and Belfry, of course, for hosting this. The board of the Sister Science Club. I'm a member of that board. My name's David Ellis. The president of the board, David Duran. David, raise your hand. It's back there. John Hutzinger, who is up in the back because he's recording this for us. He's our videographer. And you can find videos of these lectures on our website. And if you check it out, it's at sistersscienceclub.com. We're trying to keep those up to date. And there are other things about the club on the website, so please check it out. Larry Price, raise your hand.
Larry,
where are you, Larry? There he is. And Joe Sherry, and there he is. And Joe and Larry and I work and try to find speakers like Professor Safran to come and speak to the community. So it's really fun to do. If you have ideas about speakers, people you know or that maybe heard elsewhere, track us down, Larry or Joe or I, or go on the website, send us an email, and we'll try to follow up on it. Dave Johnson, is Dave here? I didn't see him. Is Jocelyn here? There he is. Hey, Dave. And is Jocelyn Blevins here? I don't think so, but she's also on the board. She's a teacher at Sisters Schools. And then I want to thank Peyton, our sound person, and a new addition as of the last Frontiers of Science lecture, Dana Greenblatt, who's also back in the back. Dana does a great job keeping things running for us, so thank you. Let's see. Oh, also, Karen Sweeger and Ann Richardson, who greeted you when you came in. A big round of applause for them.
Yeah.
And whoever set up the chairs, thank you very much. I didn't get here in time to do it. I will be here to help take them down, and any of you who have time to help me with that would be much appreciated. All right. So when I printed this out, I didn't notice that there was a picture of Liz on the back. So there she is. I think we've got the right person. A reminder, the Science Club is a volunteer organization. We're a 501c3 nonprofit, and part of our mission is to raise funds and provide money to the sister school district and science teachers to support in-classroom activities, some kinds of equipment, field trips, that sort of thing. And so on September 27th, starting at 3 o'clock at 5 Pines, at the community center there at 5 Pines, we're going to be having an event with some of the teachers from the school and some of the students who have participated in some of the activities that we've been able to help fund. We'd love you all to be there. There will be some, some drinks and some hors d'oeuvres and things like that, and a lot of really interesting information. So please try to make it. The information's on our website. I'll repeat it for you though. April 27th, 3 p.m. for a couple hours. So if you can be there, we'd really appreciate it. For the main event, Dr. Elizabeth Safran is the Associate Professor of Geological Science and Director of the Earth System Science Minor at Lewis and Clark College in Portland. I know Liz because I had the privilege of working at Lewis and Clark for a number of years, and Liz has been there for 25 years. Liz is a geomorphologist by training,
Women rock.
Yeah. And so, think floods and landslides, you know, all the good stuff. And she spends a lot of time studying in that area. And she is, as she will tell you, very interested, if not obsessed, with the Cascadia subduction zone and the periodic earthquakes that occur off the coast of our state. Typically every 300 years, but it's been 325. So the suspense is building, if not the tension. Liz did her undergraduate work at Harvard. She obtained a master's in science from the University of Washington and a PhD from the University of California, Santa Barbara. Yes. Her most recent research and work is, and I really want to do this, I haven't had a chance to play with them, she's developed video games that help her understand what motivates young people to be prepared for the earthquake. So that kind of preparedness. She's done extensive work on how rivers cut through layers of earth and rock. And there's a great book out there I was telling Liz about, if you get a chance to read it, called A Walk in the Park. It's about these two guys who get the bright idea of walking the entire length of the Grand Canyon. It's not easy. Excuse me. She's been an important member of the Lewis and Clark faculty for 25 years, as I said, and she was a recipient of the highly coveted Teacher of the Year Award presented by the undergraduate students at the college. So to have that award given to a science teacher in an undergraduate population of maybe 2,200 students is really something. And she was richly considered. She drove all the way down here today at the beginning of her spring break to be here with us tonight. And she has to drive back tomorrow because she has a very large stack of papers to read. So there's no rest for the weary. But anyway, let's give her a big hand. The sisters welcome.
Thank you very much, David. I think actually my work is done. You all can go home now. It's a very lovely introduction. And so David has talked about my background. I am a geomorphologist, so more like women are dirty, I guess. That's geomorphology speak right there. And so I am not a seismologist, so why am I talking about earthquakes? I'll tell you how it happened. So I teach at this small liberal arts college, right? And I'm in a highly interdisciplinary program, environmental studies, and I started teaching this class, which I call parentheses on natural disasters. And, you know, I went to graduate school in Washington State, and I knew all about Cascadia and so on, but it wasn't until I started teaching that class and putting this disaster in the context of other disasters that have happened in this country and around the world that I sort of came to appreciate the jaw-dropping sort of pre-disaster moment that we're in. And I decided I had to sort of drop everything else and start to really think about that and trying to engage people in thinking about that disaster. So the title of this talk is Reckoning with the Really Big One. And the title refers to a 2015 New Yorker article by Catherine Schultz, which was entitled The Really Big One. And this is the art that accompanies it. Has anybody in the audience read that article? Yeah, it was quite the thing in its day. And it focused, as will I, on what geologists refer to as a mega thrust earthquake. Yeah, geology is full of like innuendo and all kinds of fun terminology. All the world's largest earthquakes are of this type, and they're generated along a type of plate boundary called a subduction zone, and we live near one. It's the Cascadia subduction zone, and one day it's going to produce a magnitude 9-ish earthquake. In Schultz's article, a FEMA official infamously said that when that happens, quote, everything west of I-5 is toast. That person caught a lot of flack for that remark. So, if this hazard is so alarming, why don't more people know about it? Why aren't we all running around talking about this all the time? Well, I am. Why is this talk even necessary? So I'll start by explaining that, then I'll discuss the causes of the hazards, then I'll describe some of the anticipated impacts, and then at the end I'll just touch on some of the things that are being done or can be done. So how is this a surprise? The answer, I think, comes in a couple pieces. The first is an absence of first-hand experience. So the last one of these megathrust earthquakes happened 325 years ago. And here in Oregon, unlike in California, we don't have a lot of small to moderate-sized earthquakes to remind us of this seismic hazard. I was lucky enough to spend 3 months in Japan on my last sabbatical, and I felt 7 earthquakes during that time. Over 25 years of living in Portland, I felt 2, right? So it's quiet. There is no written record of the last event because the people who lived here at the time, Native Americans, didn't keep such records, although there actually were oral records of this event and the attendant tsunami and stories of battles between thunderbird and whale. But they were not recognized as such by subsequent settlers. So you might have thought that geologists, at least, would know about this based on our tectonic studying. But here's a mind-blowing fact for all of you. Plate tectonics, the unifying theory of geology, is a baby. It's barely 60 years old. Yeah, so a lot of infrastructure was developed before plate tectonics came along. And even after plate tectonics came along, the quietness of this subduction zone was kind of a mystery. And it was a little bit, people didn't quite know what to do with it. There were some ideas that maybe the subduction zone had stopped, or maybe that it was lubricated by lots of sediments and it wasn't generating earthquakes for that reason. None of that actually turned out to be true. Oops, excuse me. So let's talk about plate tectonics. And we can sort of segue into, what is this all about? So, Earth is a layered sphere. The outermost part of the sphere is brittle, and it sits on a more plastic layer that is capable of moving. The brittle layer is broken into pieces, and those are what we call tectonic plates. This is a map of the world's plates. Let's see if I can make this thing work. You are here. This is our special little bitty plate, the Juan de Fuca plate. And there are about a dozen, as you can see, major tectonic plates, and they skate around on Earth's surface, interacting with each other in 3 different ways. There are places where the tectonic tectonic plates pull apart from each other. There are places where they come together, and there are places where they slide past one another in the plane of Earth's surface. We're going to take a closer look at our little neighborhood, and the next slide is more or less kind of a cross-section or a vertical slice through the Juan de Fuca plate, a cartoon thereof. So on the left here, again, the map view zoomed in on our little baby plate. And then on the right is what's happening sort of underneath. On the left edge of the Juan de Fuca plate, so that is right there, is one of these areas where plates pull apart, and it's called a spreading center or a mid-ocean ridge. New plates are formed there, and over time they move away from that place, and they get older and colder the farther away from the mid-ocean ridge they get. In our neighborhood, a rock that is born at the mid-ocean ridge doesn't have very far to go before it encounters North America, which is on its own. It is its own tectonic plate. So when two plates meet in a dark alley, one of them goes down. And when one plate is capped with seafloor and the other is capped with continent, the one that is capped with seafloor is the one that goes down. And so it sinks back, the Juan de Fuca plate, therefore sinks underneath North America, down into the mantle, where, you know, in millions of years it eventually disappears or gets recycled. And this process is called subduction. Are you all with me so far? Yep. Okay, good. Now, subduction has lots of consequences. One of which is the generation of volcanoes, but that's a talk for another day. Another consequence is earthquakes, because subduction is not a smooth process. Rocks are rough, plates are rough. The sliding, so-called sliding, of one plate beneath another is really a process of lurching, of getting stuck and unstuck at the interface between the plates. And the unsticking is what causes earthquakes. So in the early 1980s, some geophysicists began trying to characterize the magnitude of subduction zone earthquakes in a systematic way. They plotted great earthquakes of the world and their magnitudes as a function of the rate of plate movement on the y-axis there, and the age of the subducting or downgoing plate. These two things are not wholly independent, since the age of the plate when it gets subducted is partly dependent on how fast the plate is moving, but it's also dependent on how far away the plate is from its birthplace at the mid-ocean ridge. And these geophysicists found that there was a maybe sort of pattern there, with the youngest plates and the fastest plate motions giving rise to the very largest earthquakes. This plot contains events that actually happened, except for this dot, which is kind of a "you are here" type of dot. That is the Juan de Fuca plate on which no earthquake had been recorded. And although aspects of this plot have since been critiqued and disputed, and more things have happened since it was created, this was kind of a seminal moment when and the magnitude of potential earthquakes on the Cascadia subduction zone began to be appreciated, right? The potential magnitude of these events. And it spurred a generation of geologists to go looking for evidence of past earthquakes. And they began finding it. So let's explore some of it. So to understand the various forms of evidence, we need to look in more detail at what happens during subduction. So I already said that subduction is not a smooth process. And this pair of diagrams illustrates that. So during the period between earthquakes, or the interseismic period, that's the one up the upper diagram there, the two plates are actually locked together for part of their contact zone. But that doesn't stop the subduction. You can't stop plate tectonics despite what the t-shirts say. The downgoing plate is like an anchor, right? Anchors away, it's sinking inexorably back into the mantle. And so as that movement progresses, the overlying plate that it's stuck to has no option but to get deformed. It gets bent. And this is literally measurable with GPS or global positioning system technology today. We can observe parts of North America getting squeezed together and lifted up. And notice that as I do this, the place where my knuckles are is rising, but my fingertips are getting depressed, right? During the earthquake, when the earthquake happens, the overlying plate snaps back, and you can practically hear it go boing, like that. And look what's happened. My knuckles have gone down, but my fingertips have gone up relative to where they were before. So that's this lower diagram here. So effectively, instantaneously, or in the space of a few minutes, the coastal landscape rearranges itself. And there are places that drop down and other places that lift up. And we can find evidence of both of these things. So the dropping down means that some areas that were above sea level are now below sea level, and you get these things like drowned forests. Conversely, sometimes you get things like corals being uplifted beyond sea level, and that's the lower photo there on the right from an earthquake that happened in Indonesia in 2005. Those corals are dead now because they're above the water. So let's take a little closer look at this drowned tree scenario, because we see a lot of that in the Pacific Northwest. So in this, on the far left, you have this happy coastal forest, which maybe has a mix of cedar and spruce trees. Next thing you know, an earthquake has happened, and suddenly those trees are underwater, at least during high tide. Right? Trees don't like that. They tend to die when that happens, and that's what's happening in that second panel there. Because this place is now underwater, at least some of the time, sediment starts to get deposited there, and the bases of the trees get buried over time, and that's the mud that's encasing the lower parts of these trees. Spruce is not very resistant to decay, so the spruce trees disappear except for the part that's buried in mud. The cedar trees are more resistant to decay, and sometimes you'll see them, there's snags sticking up above the mud level. Eventually, because of sedimentation and because the seismic bending cycle begins all over again, that area becomes land again, and you see plants colonizing it and so on. And on the right here is a photo of all of this. You can see one of those spruce stumps, and really importantly, you can see the roots of that stump. The roots are buried in the soil and always have been, and when those trees get inundated, the roots tend not to decay, or to decay only slowly, because they're, unlike the trunks, not exposed to much oxygen. So if you're really lucky, you can do dendrochronology, or tree ring counting, on those tree roots and figure out when that tree died, and thus get an age on the earthquake that caused the subsidence. And I can explain more details about how that happens later if anybody is interested. So note, by the way, this rather abrupt transition to mud from whatever this buried soil to mud transition, because this next photo shares that attribute, but also shows us another piece of evidence for these past events. So the sequence here is we have some older dune sand capped by this topsoil, which is full of organic material, and actually was also included some refuse and was likely amended soil, because this area was used. These are fire pits that were used by Native Americans. They contain fire-cracked rocks. So it's clear that this was, once upon a time, the land surface. That layer is overlain by a sheet of sand. And that sand is interpreted to be a deposit from a tsunami, which brought sediment from the sea to the land instead of from the land to the sea, as we normally observe. And then on top of that sand sheet is mud, right? So mud again, meaning that land was underwater now, had undergone sinking or subsidence, and so now was getting slowly covered by mud, and again, eventually got raised up again above sea level and, is growing grasses and things. Does that make sense? So, sand sheets, another piece of evidence of past earthquake and tsunami. Okay, here's a completely different line of evidence. So those drowned trees and tsunami sheets allow us to go back a little bit in time. If we want to go back further, we need a longer record. And the longer record comes from sediments that have accumulated on the sea floor. So this is quite a story, and I highly recommend that you listen to, find a YouTube video by Chris Goldfinger, who tells the story of this in great detail. He was one of the figures who put together this beautiful story. But I will give you the gist. So you can appreciate that on land there are branching networks of rivers that occupy channels, right? There are actually such things under the sea too, on the edge of the continent and sprawling across the sea floor. And those submarine canyons funnel sediment, which occasionally gets dislodged from the continental shelf and flows in these submarine landslides called turbidites down these submarine canyons. So sediment falls off in one place, flows a long way, and gets deposited in another place, just like landslides on land. And these turbidite deposits, these submarine landslide deposits, have a characteristic look to them because the coarser grains settle first, and then the finer grains take their sweet time settling out on top of that. So there's a kind of characteristic look to this type of event if you were able to sink a core into the sediments and pull it up and look at it. And various marine sedimentary geologists have been doing that for their own reasons and publishing about it when a geologist named John Adams noticed some fascinating patterns in the data about these sequences of submarine landslides that these marine sedimentologists had published. What John Adams noticed was that in each of these sort of tributaries, if you will, to this underwater network of channels, where the cores had been taken from various tributaries, he was intrigued to notice that the number of these submarine landslides was pretty much the same. It was the same in this tributary and that tributary and this tributary, and moreover, it was also the same right here, where they all came together. Now this is an odd thing, because you would think that if submarine landslides were being generated by a variety of processes, which they are, sometimes sediment will just pile up too steeply and randomly fail, or sometimes there's a little tectonic movement locally, or sometimes there's a storm. Then you would expect to see different numbers of submarine landslides in each of the little canyons. And you would expect to see that in the sort of main trunk, it would be additive, right? That the main trunk that's receiving all these inputs from each of the little tributaries would have more of them. But what John Adams noticed is that these all had the same number and this had the same number, and he surmised that that was happening because all of the submarine landslides were happening at once and in a very short period of time. So he surmised that this was an earthquake-triggered event, right? And so Chris Goldfinger sort of took up this idea and spent many years sort of fleshing out this question and exploring John Adams' hypothesis, not only in this area, but in these canyons as well, all up and down the Cascadia margin. And in this way, Chris Goldfinger was able to observe that John Adams' hypothesis was correct, that there were groups of locations that had very similar records, and that when he dated those events, they correlated with each other in time as well. So he discovered something further, which is that the ones that tended to stretch all up and down the coast were the thickest ones. And they seemed, therefore, to correspond to the biggest events. And from this data, Chris was able to put together a movie. Let me see if I can actually do this. All right, you might have to put up with a YouTube ad. Oh no, tragedy. Okay. Sorry. Actually, yeah, this, Peyton, where are you? Peyton? Okay, Wi-Fi. Yes, I'm not connected to the Wi-Fi. Okay. Let me see. I do so want to share this movie. Okay, but I'm moving on. What emerged from this was that there were a number of events that spanned the entire Cascadia margin, and those are the biggest, right? The size of an earthquake is proportional to the area of the fault that slips. So the longer the fault, the bigger the earthquake. So what Goldfinger observed was that many of the earthquakes in the history of movement on the Cascadia margin actually only affected a part of it, but there were quite a few that affected the entire thing. And that is sort of summarized roughly in this diagram here, which shows now a 10,000 year history of earthquakes on the Cascadia subduction zone. So this subduction zone went from being the least well understood to now being one of the best well understood subduction zones in the world. And so what I want you to notice, not only are there bigger ones and smaller ones, but the spacing of these events is not at all regular, right? We wish that we wish that it was otherwise, but we cannot predict earthquakes. And so, you may have a sense that the Cascadia subduction zone earthquake is quote-unquote overdue. And in a sense, it is true that the time since the last one is longer than the average recurrence time on the southern part of the fault. But the northern part of the fault doesn't fail nearly as frequently. So it depends where you are and how big of an earthquake we're talking about. So we can express the probabilities of occurrence of the earthquake as being something like 35 to 40% of an 8-ish in the southern part, and something like 12% of a 9 on the whole thing in the next 50 years. Those are the probabilities that have been published. Okay? Much depends on whether these earthquakes are clustered or not. Some people argue that rather than being regular, they come in groups. And if that is true, and this is the last group, then we could be in trouble. Because there might be one more in our cluster, and that would raise the probability significantly. Okay, I want to talk just a little bit more about the most recent of these events, which was one of these magnitude 9-ish, a big one, a really big one. So it happened at around 9 p.m. on January 26th in the year 1700. if a geologist ever says something like that to you, you need to pound your hand on the table and lean across the table and look them in the eye and say, how do you know that? You can't know that, right? Because nothing, no geochronologic technique is ever going to be that precise, right? This smacks of human recorded history, right? But I've already said that people here were not writing things down at that time. So how do we know the timing of this event with such precision? Japan. Brilliant. Just because you weren't writing things down doesn't mean nobody who was affected by this event wasn't writing things down. Oh, the double negative find. So sorry. Okay, on the other side of the world, written records were being kept. This is an example of an entry from administrative records that were kept by district magistrates of a feudal domain. And among the meticulous details contained in these records is a mention of the coming of a tsunami one day that was not preceded by an earthquake. It did damage in various places, and the location and extent of that damage was carefully recorded. This was true for several different locations in Japan, and the story is detailed in a wonderful publication called The Orphan Tsunami of 1700, which is freely available online, written by Brian Atwater and his Japanese colleagues who pieced together the story. So to understand where the parent, the orphan's parent was, we need to go back to thinking about tsunamis. So on the upper right is this cartoon about the interseismic and the seismic periods, again, co-seismic periods. What we didn't talk about earlier with the boing-oing and all that was the fact that the snapping back of the plate occurs underwater, right? And so when the plate snaps up, it lifts a giant pile of water with it, which then collapses and oscillates back and forth, creating a train of waves, and not just one, rippling out in all directions. And I guess I can't show you this because I am not connected to the Wi-Fi, which is really sad. What this means is that it gives us tools to try to understand what happened in Japan. So, armed with the patterns of tsunami inundation documented by those administrative records, tsunami scientists tried to model the patterns of waves that would be generated by various possible earthquake sources all around the Ring of Fire. The Ring of Fire is like 100 loaded cannons, right? All capable of producing the same kind of giant earthquake and tsunami. And they found that the best match to the Japanese records was from an earthquake source on the Cascadia subduction zone. So the black bars are the documented run-up based on the Japanese records, and the gray bars are what the tsunami models suggested would happen in Japan from a Cascadia subduction zone earthquake. Does that make sense, everybody? Okay. And it's a pretty good match. It's a much better match than any other source. So tsunamis can travel across the entire Pacific Basin in a matter of less than a day. They travel at hundreds of kilometers per hour, And out at sea, they're like this tall. It's not until they get close to shore that they begin to slow down. The front end of these very long wavelength waves begins to slow down and pile up. And the tsunami inundation that results is like an extremely high tide that you can't escape. So the peaks and valleys that these multiple waves introduce make it unsafe to be on the shore, not just immediately after a tsunami occurs, but for maybe 24 hours. So what does all this mean for us? It means that one day this will be us. This is a scene from the 2011 tsunami in East Japan. And when this happens here, the tsunami component of the event is likely to be the most devastating part of it. We are lucky that along many parts of our coast, it is possible to get to high ground within about 15 to 30 minutes, which is what we'll have. But this tsunami evacuation map from Seaside shows that it's not going to be easy or possible everywhere. If you're on the beach in Seaside when this happens, and you have to get to the green zone over here, you're going to have to cross 2 creeks to do so. And the bridges may or may not be there, right? Vulnerable structures. So, by the way, just as we can affect Japan, tsunamis generated in Japan and other places can affect us. So the orange-colored areas on this map are places that could be at risk from a large, distant source of tsunami, right? Those won't be as big, but they still could be harmful. In terms of shaking associated with the earthquake, we can expect that it will last 2 to 3 minutes. And that it will be strongest along the coast and sort of die off the further inland you go. Even here in Sisters, though, you could still experience strong to moderate to strong shaking. And in Portland, I will experience strong to severe shaking. Hopefully, you will only experience slight damage overall if you look at the, what does strong shaking mean. But Portland will experience some significant damage to certain kinds of structures. And one of the most susceptible kinds of structures are unreinforced masonry buildings, or URMs. This image is from, unlike wood-framed buildings, these URMs have no ability to withstand shear forces, which are common in earthquakes. And the 2010-2011 series of earthquakes that struck Christchurch really illustrated how vulnerable these URMs are to earthquakes. This image is from that set of events, which really destroyed the downtown core. Both Portland and Seattle, and even Bend, have quite a few of these URMs. There are several geologic conditions that can exacerbate the damages caused by shaking. In hilly areas, landslides will be triggered. This will affect the Cascades and the Coast Range, very severely inhibiting efforts to respond to the coastal and valley communities by emergency responders. The composition of the ground can also affect how strong shaking feels, which is what's shown in these 3 seismograms from the Loma Prieta earthquake of 1989. These 3 sensors were all quite close together, but this one was on bedrock, while this one was on weak bay muds. And you can see how much more shaking there is associated with that. And this situation on the right is something called liquefaction, which is when sediments that are wet or saturated get shaken. Sometimes they can flow. Have you ever stood on the beach, on the firm sand, right where the waves are coming in, and like jiggled your feet up and down? Maybe it just me. Yes, you have. What happens? You sink. That's liquefaction. What you're doing is you're causing the sand to liquefy by agitating that saturated sediment. So as you can see, entire apartment buildings can sink into the ground this way. You can explore to your heart's content the statewide susceptibility to liquefaction using this cool interactive map called Oregon HazView. I've pulled up your hazard and mine side by side, no floating. Even way out here, you have moderate susceptibility to liquefaction, while large parts of Portland have very high susceptibility, especially the floodplains of the Willamette and Columbia rivers. Well, this is a problem because there's a lot of infrastructure built in those places, like, hello, there's the airport somewhere over there, freeways, bridge footings. So this is a simulation of the Burnside Bridge's expected performance in a magnitude 9 earthquake, which gives us a sense of what to expect and tells us that communities are going to be isolated by these broken transportation corridors, and ordinary roads are not going to look so great either. And other types of infrastructure, think about it, cell towers, power stations, water and sewer and pipe networks. And because if this is a magnitude 9 earthquake, it will affect the whole region. So for those reasons, it is expected that essential services will take many months or even years to restore in the Willamette Valley and the coast, according to the Oregon Resilience Plan, which was a seminal document published in 2013. Notice, lucky ducks, areas east of the Cascades are not included in this table. What you can expect is that this region is going to be a staging area for resources and responders flowing in and evacuees flowing out eventually, we hope. But wait, there's more. You will be affected in unexpected ways. For example, 90% of the liquid fuel for the whole state of Oregon is stored along this stretch of the lower Willamette River near its confluence with the Columbia River. And the fuels are stored in dozens of tanks like these, which are parked on these highly liquefiable soils. Some of the tanks are nearly 100 years old. And by the way, there's also a local fault that runs at the base of the Forest Park, which itself is a possible source of landslides and of wildfire fuel. So basically, there's no place worse you could have put these tanks full of flammable fuel. In an earthquake, these tanks could rupture, and the size of the spill would dwarf the Exxon Valdez and rival the Deepwater Horizon spills. Moreover, there is a high potential for fuel ignition if that happens, which has direct impacts in the form of fire and indirect impacts from particulate plumes generated by the smoke. And there's been extensive work on this and some modeling to show how different populations in the city of Portland might be affected by that. Unfortunately, that type of cascading disaster is not the only one that we could face. There are lots of nasty chemicals stored in various quantities throughout the state that are used for industrial purposes, things like hydrochloric acid or ammonia or chlorine. These so-called Tier 2 facilities are ones that store enough of these nasty chemicals to be required to report them to the EPA. And unfortunately, many of those facilities are sited on highly liquefiable soils. A recent study that focused on just 4 such facilities in the Portland area, that's the panel on the right there, modeled the kinds of toxic vapor plumes that could be produced under various wind conditions if there were earthquake-triggered releases. And I don't know if you can see this table down at the bottom, but there could be up to 2,500 fatalities associated with such a release. Are you feeling this way right now? Are we all doomed? Can anything be done? Can any individual make a difference? The answers are not entirely. Yes, and yes. So I want to end kind of on a somewhat more cheerful note by talking about just a couple of examples of infrastructure upgrades that are happening. Again, a lot of things are happening. These are just 3 little examples. The Burnside Bridge is slated to be rebuilt, hopefully by the early 2030s. The design phase is just wrapping up now to serve as the lifeline between the east and the west sides of the Willamette River. The Burnside Bridge, interestingly, was chosen because of all the east-west roads, it has the fewest overpasses above it. So it really could be a lifeline to connect the 2 sides. Portland Airport has plans underway to make at least one of its runways resistant to liquefaction. And a few vertical evacuation structures are being built in Washington and Oregon to support populations that won't be able to make it to high ground in time during a tsunami. Incredibly importantly, in 2022, Senate Bill 1567 was signed into law. This gives the Department of Environmental Quality authority to develop a seismic fuel tank stability program and gives them oversight over that CEI hub. So under this, they are developing a process and criteria for seismic vulnerability assessments and mitigation plan development. And all of the fuel tank owners or operators will be required to mitigate the seismic hazard on a 10-year timeline once their mitigation plans are approved by the DEQ. So that's a good, important step in the right direction. We also now have an earthquake early warning system. This does not tell you when an earthquake is going to happen. It tells you when one has already happened. You might think you don't need that kind of information, but actually this system takes advantage of the difference in speed between different earthquake wave types, and it can give people a certain distance away from the epicenter a few seconds warning that destructive shaking is headed their way, which can be enough time to take some protective action, like drop, cover, and hold on. The The Oregon Office of Emergency Management urges everybody to be self-sufficient for at least 2 weeks. So this means water, sanitation, food, medications, shelter, and other essential supplies. Because of the regional nature of this event, it's going to take a long time to get help. And the more people can help themselves, the more attention responders can devote to dealing with some of the really hairy things that I've talked about in this presentation. You can also become a trained volunteer. And if you're thinking like, ha ha ha, I live in Sisters, most of this won't affect me, do this. Become a CERT, a Community Emergency Response Team member. This CERT training can help you learn how to be a useful person on the scene of a disaster. It turns out that after disasters, most people are rescued by their neighbors or people who just are happening by, not by first responders. And this training helps, which is about 30 hours long, helps you do so in a way that minimizes injury to yourself. And lastly, less tangible, but in my mind, very important is this. We do not have an earthquake culture built on experience. So we have to create our own earthquake culture from borrowed experience and from our imaginations, informed by fact. We need to be thinking about this inevitability and integrating it into our lives and what we do. So if it's a novel, or a nonfiction book, or a song, or a work of art, or even a conversation, make this a part of your culture. For the last few years in my research, I've been working in an interdisciplinary team consisting of a geologist, a psychologist, a media scholar, and a computer scientist. And as David mentioned, we've been using custom-built video games as tools in experiments to try to understand what motivates 20-somethings to prepare for earthquakes, or not, as the case may be. At the same time, we're learning about what people can get out of engaging with this content in the form of entertaining-ish media. We think of learning as happening in lectures and classrooms, but legitimate learning can and does happen everywhere, from all kinds of sources. And the more we build this content into the types of sources that we willingly seek out, the easier it will be to develop the earthquake culture that we so badly need. Thank you for playing.
So we have time for some questions. Don't look at your watch. It's not really so. It's heavy stuff. And so raise your hand. Question over here.
So the tsunami will come off the Columbia River, but it will die out completely by Longview. That's the expectation. So it's not going to get to Portland.
Are you using artificial intelligence yet to in your assessments?
I don't even have any real intelligence yet. I am not. But in my assessments, remember, is of the intelligence of 20-something-year-olds vis-a-vis earthquake preparedness. So no, I'm not yet using AI.
Similar to California, is there like retroactive kind of rebuild and reinforcements of some old structures, or
Oh, quite a question.
have they rebuilt the building codes to
Yeah.
like 30 years ago to make sure?
Yeah, so the building codes have gotten better and better. So when people ask me if their building is going to hold up. I always say, how old is your building? First of all, I am not a structural engineer. Secondly, how old is your building? So there was nothing before around 1974. And then there was a little something, but not much. The building codes started to reckon with these hazards in around the mid-90s and got considerably better in the early 2000s. So after 2000 is good, and after 2004-ish is even better. But it should be noted that, number one, most wood-framed buildings, like single-family residences, come through earthquakes pretty well. So those structures aren't going to like collapse on you and pancake, right? The other thing is that the building codes are basically life safety codes, so that you can walk out of the building after the earthquake. They don't mean that you can walk back in and start reusing that building, which is unfortunate.
Back.
Yeah, is there an order to how plates move around the globe?
Oh, that is a good question. Yeah, what the heck? I mean, they move at different rates, and crazy things happen, like plate boundaries can get reorganized if, let's say, subduction is happening, right? Here's my subducting plate. And what happens if a blob of continent reaches the subduction zone? Right? It can't go down because continents are too buoyant. So if it meets another continent, it will make a big collision zone. Like, where is this happening in the world? The Himalayas, right? India just sailed right on into Asia and is crunching the crust, which is, by the way, squirting around the edges of India in these long strike-slip faults. It's crazy. But if there isn't another continent, right, on this plate, crazy things can happen, like, maybe the subduction will reverse direction, or a strike-slip fault will develop through that little blob of continent. So things are happening all the time, my friend. And actually, even the Juan de Fuca plate, is getting smaller and smaller all the time. You know why? Because the San Andreas is migrating northward. Yes, that's right. That's right. Someday we're going to be entirely taken over. That little piece will be consumed. We'll all be along the San Andreas fault.
Over there on the side.
You talked about this just a little bit, but just so folks know that FEMA has identified Central Oregon, in particular the Redmond Airport, as a regional center. The reason for that is so that C-130 cargo planes, one of the few places they can land, and helicopters can take off here to do search and rescue on the other side. So there's been a lot of work that's been done by the city of Redmond, Michigan County, and FEMA to identify this as a regional facility that will have hospital, food distribution, all kinds of things.
Yes.
And it's all here in Central Oregon.
Yes. So get trained as certs, people. You can be really helpful when all that is going down.
Two more.
What do you call it? Too much pressure for me.
So when you were talking about the trees, the ghost forests and the stumps that are buried,
Yeah.
you can tell by the rings how old the trees were
Yeah.
when they were died, but how do you tell how long they've been buried?
That's such a good question. Okay, so here's what you need. You need one tree, big tree, that's still living. So, you know how tree rings, there's one for every year, but they're not evenly spaced. Do you all know this?
Yeah.
Right? So, okay. they'd be like, yeah, don't talk about it. So the spacing of the tree rings reflects the unique climatic conditions during each year and so on and so forth. And so it's kind of like a barcode, right? It's like an organic barcode. So if you have one really big old living tree and you can look at its barcode, then you can look at the tree ring record of the roots of the dead tree, and you can look for overlap in the barcodes. And then you can count backwards from that living tree all the way to when the dead tree died. Yeah. I know, isn't it fun?
One last question.
Back here. So if we look at a timeline here, is the longer before we get a quake, increase its intensity, and if I could ask a double question, does sea level rise, if it takes another 50, 100 years, to have an impact?
Okay, so the first part, so is the longer between events bode ill for the size of the subsequent event, if I understand your question? Okay, so that model is called the slip predictable model. So that the slip predictable model is the longer the interval before an event, the bigger the event is going to be. There's another model which is called the time predictable model, which is the bigger an event, the longer it's going to be till the next one. Both of those models have been explored in various settings, and they're not really good. So, this is the problem, people. Earthquakes are truly not predictable. It's infuriating that this has eluded the geophysical community. But there may be certain places where one or another of those models is good, but generally speaking, that's not a safe bet.
And part two?
Oh, and part two was, will sea level rise affect things? Well, yes. I mean, because you get that co-seismic subsidence, and then sea level is higher, then, more will be inundated. But presumably, hopefully, something, people will be scurrying out of the way by then.
So Liz, it looks like maybe we could play that video.
Nice.
If people are interested in seeing that.
Yes.
It's a few minutes long.
This is the,
Not sure. Cascadia Rupture Series 2012.
okay, so you could probably, I'm not going to control this. You could probably play it at like 1.5
Slides.
I would say.
Lights.
It's just kind of cool to see it all laid out like this, I think. And you get a real sense that, the southern part of the subduction zone just gets hammered over and over and over again, because it's involved in all the big ones, but it's also involved in all these little ones. Yeah, I know, like, you don't want to be living in Bandon, I'm sorry to say.
Is that the San Andreas at the bottom?
Yes, the San Andreas starts here. Uncertainty is infuriating. It does. Okay. There's the San Andreas firing off. There it is, people. 1700 event.
Thank you, Liz.